All right, so we continue with the same class, and we'll talk about Markov models for text and music, and we'll jump, or I mean, the highlight will be this Lamp-Ziff algorithm and musical style, which is included in your homework assignment. So what are Markov models? Okay, so Markov model is basically a description of a process as some kind of a finite state machine. Okay, so these are the states. The machine is described by the transitions, and it's a probabilistic finite state machine, which means that if you are in each one of these states, the number you have here on the transition is the probability of moving from A to B. So in this simple example, think about your space is three-dimensional, and each one of these will be encoded as maybe 1, 0, 0, 0, 1 if you're here, 0, or here it will be 0, 0, 1. And then you kind of switch from state to state by following this probability distribution. Okay, so let's do a little experiment. So let's say we start with state A. Okay, so state A will be encoded as 1, 0, 0. Okay, so if we're here, okay, what we have is we have a probability of going with 0.1 to B. We have probability of 0.9 going to C. Okay, and we have zero probability. There is no returning loop here. Okay, I mean, in this matrix, everything here is zero, so there is no way you can jump back to A. But I mean, in general, you can also return to the same state. Okay, so it would represent the fact that we are in state A. We'll represent this as a vector 1, 0, 0. And if you want to multiply this, so basically what we'll do is, take here this S0, right? And this S0 will be a vector of 1, 0, 0, right? And it depends on the convention of how we describe or how we write the probabilities. In this case, you can see that we actually use a left multiplication. Okay, so let me see. So yeah, so 1, 0, 0. What will happen is, what is the probability of what vector will get out? So 1, and this is 0. So we'll have, let me just kind of go quickly and reuse the drawing, right? So what will be the outcome? The outcome will be, for the first outcome, it will be 0, right? The second one, 1, 0, 0, we multiply here. So this left multiplication, we get 0.1, right? And for the last one, we'll get 0.9. Okay. So if we start, so what is the meaning of this? So if we started with a certainty that we are in state A, after one step, we are with 10% certainty in B and 90% certainty in C, right? So this becomes, now our state become probabilities. Now, if we do the next step, we have to take into account these probabilities. We actually we'll put this probability here, okay? And we'll get an S2 and so on. So S2 will be basically going through this probability distribution twice. So it's S0 P square and so on. And after n steps, you'll get to basically where you started with. And this matrix multiplied by itself n times for making n steps. This is kind of represented here with this code in Python. And you have this matrix here, because the multiplication is done on the right. This matrix is transposed, and I think there is a little error here because it actually gives you 0.2 on one of them, so it's not exactly the same matrix. No, it's a different matrix, sorry. But the idea is you take this transition matrix, okay, and you do basically this product, okay? You multiply your state, and the state is something that you decide where you start with. You can start at state 1, state 2, state 3, or some distribution of these states. And once you do this, you multiply the state by this matrix P, okay? So actually, in this case, it is left product, and this gives you the new state, and you keep on going through and through, and you can see how your states evolve. And this is basically the notion of Markov process. Okay, you have a transition matrix and initial state, and then you keep on kind of running through this automata with the correct probabilities and seeing where you land. Okay, now where is my mouse? I think I'm losing my mouse for some strange reason, and I cannot. Okay, got it. So let me erase this. Should be a way to erase all in one. Okay, never mind. So if I erase this and we move on to the next slide, basically what we have is the following. Okay, we can generalize the one step to something much more sophisticated, but the basic Markov property tells us that because this is the dynamics, this is the process that we set in motion, our next step, given like a long sequence, let's say we have states Sn, Sn minus 1, and so on, given that you are in some state at step n, and you want to consider your whole past, actually, all you need is to know the previous state you were in, okay? So basically, this is what's called Markov property, is that it has a limited memory. All it knows, your memory of that process is just the state you were in, which will then tell you what are the next possibilities. You don't need to keep record of all the previous steps. Once you arrive in a step, you, in some sense, you can be oblivious to how you ended there. Where you are will tell you what will be your next possible outcome. And this is called the Markov property. Basically, it allows you, if you think about this as a graphical model, whatever, I mean, the way you like to think about this, but it tells you the independence, that given the previous state, you're independent of past, which is way longer than one step back. And this is what this transition matrix gives you, written in a different way. Basically, this is really just an expression of the base rule. And this is why I think probability was kind of a requirement for this class, because I don't want to start explaining conditional probabilities. But you can see that, joint probability is basically conditional probability times, the marginal. So if we want to know the probability of where we are in stage 2, okay, we can take the joint probability and just average this on, this is on S1, okay? So if we average on S1, we end up with marginal S2. And plugging this in, we see that we average here, again, correction, S1 and S1. If we have this is exactly the matrix multiplication that we showed before. This is Pij times the probability vector of that state, okay? Having defined Markov source, I think it opens up now possibilities of including time or dependencies over time, conditional probabilities, prediction, in our considerations of encoding, entropy calculations, basically also some sort of what is the uncertainty about the next step, the prediction error. So I mentioned when we spoke about spectral flatness, a few classes ago, the idea of entropy rate. So really what we care about is entropy rate, because we said that the entropy, to be effective, actually to be able to encode something or reduce the uncertainty to something which is less than the size of the alphabet, log size of the alphabet. If we want to encode something more efficiently, we actually look at long sequences. And by dividing by the lengths of the sequence, we get kind of the average bit per symbol. Okay, so if we take this very long block encoding, this is really the entropy rate. Sometimes people kind of, I wouldn't say confused, but I mean, sometimes there is ambiguity. Are you talking about entropy rate or an entropy of an individual event where you don't take into account other events? So we'll kind of consider this idea that entropy rate is actually something which takes into account infinite past or infinite length of your sequences. It can be shown, and this is also a powerful result, and that I would like you to keep in mind, is that you could, instead of encoding very long blocks, you could encode the last event given all the past events. So basically, it's that conditional entropy which takes into account the conditional information. So this result, which tells you that you can either encode very long blocks, or you can encode by predicting the next event on the past, they give you the same result. They're the same entropy rates. Now, this rule is independent of the Markov source, okay? Just in the Markov source, we know that all we need is just 2 steps, okay? But this is a general result, okay, that any information source or any probability distribution of the sequences can be either, you can estimate its uncertainty or entropy or its complexity by looking at very long blocks and dividing by the length of the block, or considering some conditional probability, okay? So having said that, the interesting thing is about the entropy rate of the Markov source. So if we take a very long outcome from running this Markov finite state automata, this engine, over many steps, you can show that it actually arrives at some kind of a steady state, which is pi, but the probability is actually governed by something else, okay? So actually the probability depends not on the distribution of the steady state, but also on the condition of the transition probability. What it means to us is that actually we need to know the conditional probability. We need to be able to predict the next outcome, okay? We cannot just consider the steady state probability, okay? We need to know that from every state there is some kind of a likelihood that will move in certain places and will not move to another places. So we're not free just to throw a dice and choose it according to this pi. We actually have to take into account this pi ij. Now, if our sources can be of a longer Markov dimension, I would say. What I mean by it's longer or larger Markov order. I mean, this is first order Markov. This one depends on the previous one. You can also construct things that take into account 2 steps. You have tuples or triplets. So depending on the n tuples, you can have n dependency on the n previous ones. These could be all viewed as more complicated Markov sources, and the entropy would require us to know these probability transitions. So the observations here are, first of all, the entropy of a Markov model requires knowledge of a transition matrix. So to know really how to encode efficiently a Markov source, you need to estimate the transition probabilities. And if we go to higher order Markov sources, which means Markov sources not only depend on the previous one, but maybe depend on 2 or 3 or n, we will have to estimate these matrices, huge PIJs, and these are hard to estimate. So one way to deal with this is to use some tricks from actually compression. And instead of learning probability distributions by counting all possible pairs or triplets, or depending on how many past symbols you want to include to see what's your next outcome, there is this super elegant algorithm called Lempel-Ziv, LZ, and this is how it works. Actually, it's surprisingly simple. This is a compression algorithm. Okay, it takes a sequence and it constructs in a deterministic way a tree, a parsing tree. But the idea is that if you use this parsing tree and you use this for some kind of efficient encoding, Lempel-Ziv proved that you can reach with this type of encoding the entropy of any Markov sequence, which means you don't need to go and estimate transition probabilities. You can build this tree, and if the tree is deep enough and you encode using this tree, which I'm going to show briefly now how it's done, you are actually as good as estimating the entropy or encoding this as if you knew any arbitrarily large Markov source. So this is a really powerful result. I mean, it takes a while to appreciate why it's so powerful, but really, let me kind of just for a second give a motivation. If we go into text or we go into music sequences, okay, a lot of a lot of the meaning of the next letter, the next word, the next chord, the next melody depends on the previous events. So we tend to predict what's going to happen. Right now, how would you do the prediction? Well, even if you think about us having kind of a finite size of the memory, it would be still probably several symbols long, right? Now, if we have no better tool than a Markov model, it means that we'll have to keep these huge matrices of saying, this is how much I remember, and from every sequence that I remembered of that length, I will predict the next outcome. These become huge matrices. Instead of that, you create this tree, a much more compact way, and then you can use this to encode or generate. Okay, so keeping this as a motivation, let me kind of go quickly through what is the LZ algorithm. So basically, what it does a very simple trick. It goes on a sequence left to right, and then it puts a comma on any new symbol that we haven't, or subsequence we haven't seen yet. So let's assume that we go left to right with this abracadabra. And if I encounter A and I haven't seen A, I will put a comma here. Then I move to the right. I haven't seen a B, I will put a comma here. I haven't seen an R, I'll put a comma here. Now I go back and I have seen A. Okay, so if I have seen A, I just skip forward and I look at AC. Well, I haven't seen this pair AC before, so I'll put a comma here. Okay, I have seen A, but I haven't seen, I move next, D. Well, I haven't seen AD, I've seen AC, but not AD. I'll put a comma here. Okay, now I'll go to A. I've seen A. I haven't seen the pair AB. I'll put a comma here, and I haven't seen the pair RA, and I'll put a comma here. This is our parsing. Deterministic, very simple, goes fast from left to right, not very efficient for short sequences. This is why later on, people switch to other algorithms for generating sequences in music, because we actually use this algorithm for music generation, and this is one of your exercises. So if we want to represent this, and I think I lost my mouse again. Okay, kind of hard to work without pointing where I'm talking. Just a second. All right, here it's, I'll have it back. So let's represent this now as a tree, okay? So we start from nothing, okay? And then we basically use this sequence to create, the tree, and then we'll calculate the continuations first. Next, sorry. First, let's build the tree. So we start here, we have a sequence A, okay? And then, if we have nothing before, we have B and we have an R, right? Then we go again and we have the subsequence AC, okay? So we already have this tree built, ABR. We go A and C, okay? Then we go again A and D. We have A and B, and we have R and A. So you can see that this parsing, these commas exactly represent this tree. Now for compression purposes, that was enough. And why? Because, well, first of all, how it's used for compression? Well, the idea of this thing is that, let's say, if you want to encode now the sequence AC, okay, you don't need to encode. So you encode somehow A because you haven't seen it before. You encoded B somehow because you haven't seen it in R as well. But then when you see the sequence AC, you actually using this tree, you know that it points back to A. So this points back to A. So you don't need to encode A. You can just send a pointer to A and encode C. With these short sequences, it really doesn't mean much. But if you imagine, that you have seen a very long sequence, you'll have commas that come after very long blocks, okay? And only the last symbol will be the new. The whole block would have appeared before, but you would need to encode it because you will send a pointer to a previous block. And probably that previous block also only had one symbol that was encoded, the last one, and it would point back to previous code. So once you get to very long sequences that have a lot of repetitions, because here's the whole idea is that there are a lot of repetitions, and these repetitions are encoded like pointers to the previous occurrence, basically going up that tree, you start saving a lot because you don't need to encode these blocks. All you need to encode is just the last symbol that made it new, and everything before that would be basically a pointer. And Lemblin showed that this actually, as I said, becomes as efficient as entropy. Okay, so I think I'm getting a little stressed in time, so let me kind of finish this one, and we'll continue tomorrow with some of the musical applications. But what do you want to see here? Well, the idea is that, and this is another work by Mayer Ferrer, which actually used this for universal prediction. Okay, the impulsive is universal compression. But if you want to talk about universal prediction, he actually assigned probabilities to these leaves, which are proportional to the length of the tree. So basically you put a weight 1 here, then you sum this 3, you propagate here, this will be 4. So if we kind of go slowly, and I probably will repeat this next time, you can see the probabilities for continuation. So if you're here, okay, you can see that if each letter here, okay, it's not just the terminals, but also on the bridges here, on the junctions here, you assign a weight of 1. So you have 1, 2, 3, 4, okay, versus 1 versus 2. So if you're here, you kind of like tend to drop in proportion to the weight of that branch, okay? So A will go 4 out of 7 options, B 1 out of 7 because you have a total of 7 symbols, and going to R will be 2 out of 7. So this is our initial chance of going here or here or here. If you go here, you have probability 1/3 going to every next symbol. And of course, as the tree becomes deeper, this has much more meaning. But now we can think about this as generated probability. What is the probability to generate ABRAC, okay, which is maybe a sequence here? Well, it's the probability to generate A from nothing, generate B from seeing A, okay? So A, B, okay? But now, if you look at probability of R given AB, there is nothing going on here. So we will basically have the probability of R, okay? Probability of A given ABR, probability of C given ABRA. So what we have is basically these probabilities encoded here, okay? You can kind of go and check according to these trees and branches, and you can see that you generate this ABRAC with these probabilities, okay? 4 out of 7 generating A, okay? 1/3 of going and following the B, okay? 2/7 of generating R from here, okay? Probability 1 of generating A after R, and probability of 1/3 generating, because we have an A, you have generated 1/3 after C, okay? So you kind of like always shorten your context to the history that allows you to make the prediction, and you use this tree to derive these probabilities. So this becomes a generative model. You can actually use this tree now not only to plug in a sequence and tell how probable it is, you can also make a random walk on this tree and generate new sequences. So I will kind of talk about the musical applications of this thing that we did on MIDI files called LZFi, and the motives continuation, how to create the motives, how to create the continuations, which is part of your homework. So I'll return to this tomorrow, and some improvisation systems that actually use these methods to capture basically on-the-fly sequences from a musician, and then create continuations in the style of that musician. So this is all for next time. Let me stop this.
Shlomo.
Okay. Where's our... Okay, just a second. I think I'm still recording, so let me just stop the recording. And